Hello everyone, my name is Alexey Smirnov and I'm CEO and co-founder at deBridge. We provide a secure and decentralized interoperability infrastructure for Web3. And I would just like to greet everyone who is participating in this hackathon, and during this workshop I'll provide some insights on how cross-chain messaging is working, and at the same time I will probably give some ideas of what can be built using deBridge infrastructure. And at the end of this workshop, my colleague, our Solidity team lead, Alexey, will guide you through the process of the technical integration of like how deBridge infrastructure can be leveraged from your smart contract or from your applications. So let's get started. And first of all, I would like to highlight also that deBridge project itself has started as the hackathon project. So last year, back in April, we won the Global Chainlink Hackathon, and the hackathon itself helped us to bootstrap the protocol and kind of attract a lot of attention and interest from VCs, partners, and industry in general. And today we are excited to partner up with ETHOnline to help other fellow builders to build really cool DeFi primitives and Web3 projects as well. So let's get started. deBridge is a secure interoperability layer for Web3. The point is that we provide infrastructure that allows to interconnect any smart contract in any blockchain. So deBridge protocol enables seamless cross-chain transfers of value and messages across different chains. So in order to pass messages between different smart contracts, you just need to interact with the deBridge protocol smart contract, which is deployed in every blockchain supported by our infrastructure. And what is needed for cross-chain interoperability? Because bridging of assets is not enough. Like many of the existing bridging protocols are purely focused on the cross-chain swaps or value transfers. But in fact, in order to build really capital efficient cross-chain solutions, we need to be able to transfer value and messages simultaneously. And we should be able to do that not only between users and smart contracts, but also between smart contracts themselves. So that smart contract in one blockchain, let's say Ethereum, can open up positions or send a commands to smart contract in another chain. And that blockchain can be not even compatible. It can be like non-event chain theoretically. So in addition to that, we should be the receiver of the message should be able to know who is the sender. Because when we are sending the message through some messenger, like a Telegram, we can identify the sender using the ID. Same with the cross-chain messages. Like receiving smart contract should be able to know the address and the chain ID of the sender of the message itself. And the last point here, which is also important, that somebody needs to trigger the transaction on the destination chain. The transaction should be executed because any cross-chain interaction consists of two transactions, the one that initiates the interaction and the one that finalizes or executes the message on the destination chain. And deBridge infrastructure provides all these features, so you can know who is the sender, and you can also specify the small incentive, which we also call execution fee, to incentivize bots or keepers to execute your transaction on the destination chain. And I will not go deep into the technical details here, but the idea is that in order to send the message, your smart contract or externally owned account, like regular user's address, just need to call the send method of deBridge Gate smart contract. And as soon as transaction is finalized, as soon as it became irreversible, deBridge infrastructure will validate your transaction and it will be claimed in the destination chain, where deBridge Gate smart contract is called the claim method, and the same transaction deBridge Gate calls deBridge call proxy to execute the message that was passed. And basically this external call will, or like the message itself, will be passed to the receiver. That can be a smart contract, or that can be the EOA wallet as well, in case there is like liquidity transfer. And yeah, so deBridge is a secure and composable and powerful infrastructure that allows you interconnecting any smart contract in any chain. So basically, in order to do some kind of cross-chain interaction, you need to develop the sending smart contract in one chain and receiving smart contract that will receive the message and process the result of this cross-chain interaction. And one of the powerful concepts that we enable is the transaction bonding. So basically, deBridge is an infrastructure that allows to perform any complex cross-chain interaction in a single transaction. And that became possible due to our integration with the multi-send library from Gnosis. So basically the message, which has been transferred across different chains, can encode the arbitrary set of transaction calls. And when the message is executed on the destination chain, the call proxy will call the multi-send library. So together with the message, you can actually fine-tune the execution flow of the transaction and specify the special multi-send flag. If there is a multi-send flag, the deBridge call proxy will understand that this message encodes the set of transaction calls and will execute them sequentially through multi-send method, where like first call can be executed to the first smart contract, like another one will interact with the second smart contract, etc., until all the transaction calls are sequentially executed. And this kind of framework allows building very powerful cross-chain applications as well as cross-chain primitives. You can actually have cross-chain swaps to perform like conversion from any liquid asset in one chain to any liquid in another. And one of the solutions that we already have is called dswap, and we have an API that allows you to perform arbitrary cross-chain swaps. If the asset is liquid, then it can be swapped through dswap. And you can use actually dswap in order to pass value and message simultaneously. And you can do that to achieve various cross-chain needs. Let's say you can build cross-chain lending protocol where you deposit liquidity in one blockchain, let's say Ethereum, and in the same transaction, your users can draw a credit from smart contract in another blockchain, for example, Polygon. Other use cases can be cross-chain yield farming, where your liquidity is automatically balanced and kind of managed across strategies deployed in different chains. And the liquidity in each strategy can be automatically rebalanced based on the instant or like current APY of each strategy. So yeah, there are many interesting primitives that can be done. Another one is like multi-chain governance, where the voting, like governance voting, can be conducted on-chain simultaneously in different layer 2s, and then at some point the result of voting can be passed as a message to layer 1, let's say Ethereum, and can be settled. So we can collect results of governance voting, let's say from Polygon, Avalanche, Arbitrum, and some other chains, and then at certain timestamp we can settle this result in Ethereum. And that's also interesting as well, because that makes the governance voting to be very cheap and settles transaction in layer 1, which makes the overall process to be very efficient. And yeah, so in addition to that, you can use cross-chain infrastructure to combine different protocols to create money Legos, because normally we saw all these protocols to be combined within one blockchain, let's say Ethereum, where Aave is integrated with Maker or Curve is integrated with Convex. But we have not seen many examples of cross-chain solutions or cross-chain protocols that combine different DeFi primitives across different blockchains. And let's say one of the ideas would be to create the stablecoin protocol like Frax, which can open up delta neutral positions in perpetual markets in different chains simultaneously. And the protocol where the position will be open is peaked based on the funding rate. So the more, the better is funding rate, the more positions are open, right? And that allows to have this stable coin protocol to be way more capital efficient, since it's not tied or locked by one single perpetual protocol, but it can diversify the positions that are open across different perpetual markets. And yeah, so the overall idea that with having decentralized cross-chain interoperability layer, you can combine protocols and smart contracts deployed in different blockchains in order to enable more capital efficient solutions. Another direction that you can pursue here is the interoperability for NFTs and for metaverses. Since we can pass arbitrary message, we can also pass arbitrary asset, right? And in deBridge, we have the bridge for NFTs, which we call DNFT, and it's open source. You can find it in our GitHub repo. And this bridge allows to bridge any arbitrary NFTs. So you can leverage that in order to build interesting mechanics or like applications with NFTs or NFT projects. So let's say you can bridge NFT from one chain to another and in the same transaction list it in some marketplace. Or you can buy or sell game assets directly from the game interfaces without being locked to one specific chain, right? And that also allows to make assets to be interoperable between metaverses. Let's say you may have NFT from Uniswap v3, which represents certain position or liquidity provided to the protocol, and you can use that NFT as a collateral in DeFi protocol deployed in different blockchains. So it's really up to your imagination to come up with the idea of like all these interesting cross-chain scenarios. And if you have any questions about NFTs or any ideas of the projects that can be built, feel free to reach out to us on our Discord. And yeah, the last thing that I would like to mention, the new cross-chain paradigm, because like basically we saw many projects that fork themselves and deploy in different blockchains simultaneously, but with a decentralized interoperability layer, you can make your protocol or application to be globally accessible. You just need to pick one blockchain that suits your needs in the best way, and then through interoperability layer, you let users and protocols from other chains to interact with your project. Let's say users from Polygon can interact with your protocol in Arbitrum without the need to switch wallets, switch networks. And you can leverage that in order to enable global accessibility for other protocols or like for existing smart contracts deployed in certain blockchains. Let's say you can also, as a part of this hackathon, you can also combine deBridge with protocols that are partnering up with ETHOnline to participate in several sections simultaneously. You can build cross-chain application, and at the same time you can like leverage the technology or protocol, which is also part of the list of partners or like part of the technological stack. Yeah, so let's move on. The last thing that like through global interoperability layer, you can kind of let users and protocols to interact with your protocol. So you deploy your smart contract in one blockchain where you need to have like synchronous compatibility with other protocols, but then you just let protocols and users from other chains to interact with your smart contracts. And in deBridge, our goal is like to maximally facilitate this process. That's why we also provide the whole set of development tools that you can find on our website. That includes DSwap API and DSwap widgets. So basically, API allows users to construct cross-chain transactions, to build cross-chain transactions to interact with your protocol. So let's say if we have Aave deployed in Ethereum, we can do a cross-chain swap from Avalanche and provision of resulting liquidity into Aave in the same transaction. And you can also utilize DSwap widget. That's the solution that allows you to build these cross-chain interactions in your UI very quickly. So you just integrate the widget. It takes like 30 minutes or so, and then users can leverage global accessibility of your protocol from any chain where user has this, like any liquid asset. So yeah, that's a bit of the overview of what can be built using deBridge infrastructure. And again, there are so many things that can be created, and I encourage everyone to check out our documentation to see what opportunities the protocol enables. And now I would like to pass the word to our Solidity team lead, Alexey, who will guide you through more technical process of integrating with the deBridge infrastructure. And of course, I wish you good luck with the hackathon, and feel free to reach out to us whenever you have any questions. Thank you.
Hello everyone, my name is Alexey and I'm the Solidity lead at deBridge. First off, thank you all to come into my workshop. In this video my plan is the following. First, I will give you a brief introduction to the deBridge architecture, which is really important to understand to start to build and to run your cross-chain applications successfully. For instance, I will let you know how our technical stack works. I will show you how to construct a message to be broadcasted to another chain, how to monitor such message, and how to handle it. Second, I will show you a set of smart contracts that communicate with each other, leveraging the deBridge protocol in the wild. This means that we together will make a call to one smart contract with intention to finish this call on another smart contract on another chain. And finally, I will introduce our new development toolkit, which we developed to simplify the development of cross-chain applications leveraging the deBridge protocol. That's it. Let's go. First, what is deBridge from the technical point of view? deBridge is a generic messaging and cross-chain interoperability protocol. But simply speaking, this means that your smart contract on one chain can craft a message containing instructions and assets and send them to the deBridge contract with intention to broadcast this message to another chain, where the deBridge infrastructure will unpack this message and execute the instructions inside such message along with the bridged asset. So, how is this possible? deBridge consists of two layers, the protocol layer and the infrastructure layer. The protocol layer is represented by a smart contract with the name deBridge Gate, which has been deployed to every supported blockchain. Currently there are Ethereum, BNB, Heco, Arbitrum, Polygon, Avalanche, and Phantom. The same smart contract is responsible for sending messages, receiving messages, verifying them, and executing on the destination chain. Then the infrastructure layer comes into play when the message is being submitted. So when you submit a message, a special event is emitted by the smart contract. Each validator is responsible for monitoring and capturing such events from every supported blockchain, and each time the new event is captured, the validator must again verify the message, and if the message is correct, it signs it with their own private key. Then, when all the signatures are collected, they, along with the message, can be submitted to the deBridge Gate contract on the destination chain, where the contract verifies each signature against the public key, which is known and trusted. And if the signatures are correct and the message is consistent, it unpacks the message and executes the instructions inside this. That's how it looks from the high-level perspective. And from our point of view, this architecture, along with the delegated staking and slashing mechanism, makes our protocol truly permissionless and transparent. Let's dig deeper. So now let's dig deeper into the life cycle of a cross-chain call. So let's say there is a target contract which is being deployed on the destination chain, and it exposes a target method which accepts a bunch of arguments, and we want to make a call to this method from another chain, from the origin chain. How shall we do this? To construct a cross-chain call, we must make a call to the deBridge gate contract, which resides on the origin chain. The deBridge gate contract exposes a method with the name send. You can find the ABI of our contract either on our website or even at Etherscan, because the source code of the contract has been verified. You call this method either from externally owned account or from your smart contract, providing the values for each argument, specifying flags that affect the behavior of the message, and last but not least, you provide enough native blockchain currency to cover the protocol fee. The deBridge gate contract accepts all these arguments and verifies them one by one, checking if the values are correct. And if they are, the deBridge gate contract stores all these arguments as a message in its own storage. In its own storage. And if they are, the contract emits the send event, which just replicates the contents of the submission. Shortly after, the validators catch this event, and the submission enters the confirmation phase. So the validators need to wait a specific number of block confirmations for this particular transaction where the send event has been emitted, to ensure that the transaction got accepted by the blockchain. So they need to avoid network divergence. They wait at least 12 blocks for most blockchains, but they wait 256 blocks for Polygon blockchain. So after the transaction where the submission has been submitted, it got confirmed, they start validating the message. They additionally to what the contract already did. So they again validate the state, they validate the values, and if the message is correct, they sign them off by signing the message with their own private key. The resulting signatures got pulled to the deBridge storage of signatures. Currently, you can cure them using the deBridge API, so it's a centralized solution, but later we will introduce a decentralized solution like IPFS. So that's it, how the cross-chain message got submitted on the origin chain. After the submission got verified, it should be somehow relayed to the destination chain, directly into the deBridge gate contract along with the signatures that verify this submission. For this purpose, the deBridge gate contract exposes another interesting method called claim. This method accepts the message itself along with the signatures that verify this particular message. So you can see this dark blue balloon, which consists of signatures which are coming from the signature storage, which can be retrieved using the deBridge API, and the message itself, which is the same message that was submitted on the origin chain. So the contents of this dark blue balloon got submitted to the deBridge gate contract by calling its claim method. The claim method, so this process is called claiming. When called, the claim method again verifies the message and verifies its consistency by using the provided signatures. So the deBridge gate contract knows the public key of every trusted validator, and it can verify if each signature is authentic, if it comes from the known and trusted validator, and if the contents of the message hasn't been changed during submission. So if the signatures are correct, if they are verifiable, the message is marked as consistent and it got executed by the deBridge gate. how the execution is performed. The deBridge gate contract unpacks this message and takes all necessary args like receiver and call data and passes all them to the periphery contract called call proxy. The call proxy executes the instructions that it finds in the call data field, and in our case the call data field contains the call to the target method. So the call proxy makes a call to the receiver contract, it's a target contract in our case, and executes the call to the target method. After the call has been executed, the execution flow goes back to the deBridge gate, and the deBridge gate emits another event called claimed. This event indicates that the cross-chain message or submission in our case has been successfully finished. That's how the life cycle for cross-chain call occurs across our infrastructure. I believe that the only way to learn new technologies is to practice them. So now I propose to move to the real-world example, or actually a conceptual example. Imagine that we want to build a smart contract with the counter inside that can be incremented by a call from another blockchain. So for this purpose, we develop a counter smart contract. Here it is, which holds the counter property and exposes the receive increment command, which may be called by a trusted smart contract from a known blockchain. And we also build an incremental smart contract, which, when called, must craft a cross-chain message, which will be passed through the deBridge infrastructure with the segment to make a call to the counter contract. For simplicity, the incremental contract will expose a public method with the name increment, which can be called by anyone. So, in other words, there is an incremental contract which can be called by anyone, and the incremental command creates a cross-chain call to the counter contract, which can be called only by the incremental contract on the specific chain. So let's move to the code. This conceptual example I will talk about is already been built by our team and has been published in our GitHub. You can find it in our corporate GitHub account. I will show you. Yeah, the deBridge cross-chain dev example. This example is developed as a complete production-ready project, so it contains and a lot of documentation, a lot of helper scripts. It is covered with tests extensively, and of course it contains the contracts we are talking about right now. So let's move to the source code of the of each of these contracts. First of all, let's move to the counter contract. So the counter contract, as we already decided, is will store the counter internally, and here it is defined as integer, and the same contract exposes a function with the name receive increment command, which is intended to increment the internal counter property. So it accepts the amount we are willing to increment the counter by, and the initiator to the address of the wallet who actually initiated this increment. The contents of this method is very simple and straightforward. We see that the internal property is just added by the amount that has been passed as an argument. Actually, that's the whole code for this method, but for simplicity and for more clarity, I decided to add the additional event with the name counter incremented, so we can always check the logs and see who incremented the counter and when. What's more important here to mention is how the authentication is implemented. Of course, we don't want anyone to call this method. We don't want anyone to call this method either on the chain where this contract is being deployed, and we don't want anyone to call this method from any other chain. So we want some kind of authorization layer. This can be implemented using the modifier. So I give the name only cross-chain incrementer. Let's go to the implementation of this modifier. Yep, here it is, the modifier only cross-chain incrementer. So we created this modifier to prevent unauthorized calls to this particular method. This modifier is expected to prevent from any unauthorized call and give the ability to call these methods only from the chains that are supported by this contract and by trusted contracts. I mean the contracts that are allowed to call it. The whitelists are stored internally in the counter contract. You can inspect the properties by yourself. How the modifier is implemented. So when the call to this method is performed, we need to read the data from the deBridge gate contract to understand the details of this cross-chain call. For the purpose of this, you need to define the interfaces of the deBridge gate contract. You can take it either from our GitHub account. You can go to the deBridge finance account, find the deBridge contracts version 1 repository, and take the interfaces of our contracts here. Or you can use an npm package which contains those interfaces, which is very useful to plug in these contracts to your project. You can find it at npm.js. I'll show you. Yeah, here is the deBridge protocol EVM interfaces. You can just install it to your package.json file and import all available interfaces of the deBridge gate set of smart contracts. You see the imports of these interfaces coming straight from the package. The contents of the modifier is quite complex, not as easy as the receive increment command function itself, so I will describe it line by line. So first we need to obtain the address of the call proxy. For this purpose we query the deBridge gate contract, obtaining the address of the call proxy. Here is. And wrap it with the iCall proxy interface. That's how we obtained the call proxy instance. The call proxy instance is a periphery smart contract which contains the metadata of the cross-chain call during this call execution. So when the deBridge gate initiates the call on the destination chain, it injects the metadata of the call right into the call proxy. So during the execution of the call, you can get this information by querying the call proxy. The first check that we must do here is to be sure that the contract has been called by the call proxy. Again, we query the call proxy contract by calling the submission chain ID from getter. And check if the ID exists in our internal mapping called supported chains. So, and the second and the final check we must perform is to ensure that the call has been initiated by a trusted contract contract on the origin chain. For this reason, we again call the call proxy contract, calling the submission native sender getter. Mind that the native sender is represented in bytes, but not the address. This is because deBridge gate is going to support more chains, not only EVM chains, and the addresses between incompatible chains are incomparable. That's why, for compatibility reasons, every cross-chain address is represented in bytes. However, in EVM we cannot compare bytes directly. That's why we compare the hash of these bytes. So we take the hash of the native sender that we obtained from the call proxy, and we compare the resulting hash with the hash of the trusted contract that we already registered to this contract. In case they are not equal, we revert the transaction. Otherwise, all checks have passed and the execution can enter the contents of the receive increment command function. So sounds quite simple and really straightforward. Just one more thing to mention is it's up to you to decide how the counter contract should be configured. In this particular example, we've added some administrative methods like set deBridge gate, which is important for counter to query and to make some checks. And we also added add chain support, which adds the trusted chains and trusted contracts on these supported chains. But you can move this configuration anywhere, like you can move it to constructor, or it's up to you to decide how to design this. So that's how the counter contract is implemented. Let's move on to the incremental contract. So again, the incremental contract is responsible for crafting the cross-chain call. Most of its code is related to crafting a call to the deBridge gate send method. So for simplicity, we implemented two methods. The increment method, which can be called by anyone, so we don't design any restricting modifiers. And there is also a pair method with the call with the name increment with included gas. The included gas or the execution fee is a portion of the asset you are going to breach. You are willing to pay to the executor on the destination chain. So say you breach one Ether to Arbitrum. And the cost of the execution of the transaction on Arbitrum will cost, say, 0.1 Ether. So you can specify the included gas as 0.1, and the protocol is the design of our deBridge protocol. It will pay this exclusive amount to the claiming service, who will broadcast and execute the transaction. Treat it like a prepayment for gas for the destination chain. So again, what does this method do? It accepts the amount you are willing to increment your counter by. Then it encodes the call to the counter. By calling this internal method, let's inspect it. Here it is, encode receive command. The method is quite simple. You see that it takes the interface of the counter and encodes the call to receive increment command by taking its selector and by passing the amount that you specify when calling the increment method. So, in other words, when you want to increment the counter, you specify the amount in the origin chain, and this amount is being broadcasted along with the call to the destination chain where the call is performed. So when you ABI encode the call, you should wrap it with the message and pass to the deBridge gate. So here is the call to the internal send method is performed. Let's inspect it as well. The send method is more complex than the receiving method. First, we must check that this contract, the incrementer contract, has received enough asset to cover the protocol fees. So the deBridge gate takes two kind of fees. The fixed protocol fee, it is measured in the native blockchain currency of the origin chain. You can take it costs typically about $1, but in the currency of native blockchain. So, for example, for Matic, it's about 0.5 Matics, and for Ethereum, by the I don't know the exact number, but you can always obtain the exact numbers by querying the deBridge gate's global fixed native fee getter. So I suggest you to do this right now. So let's go to Etherscan. Let's find the deBridge gate contract. deBridge gate. Yeah. deBridge gate contract. The source code of the deBridge gate contract is verified, so we go to this tab. We select the writer's proxy tab, or reader's proxy. And here we find the getter with the name global fixed native fee. Global fixed native fee, here it is. And we see that the fee to send the message from Ethereum is this one. Let's take it, let's copy it and open the calculator. Yeah, so that's the amount you need to supply to deBridge gate so that deBridge gate accepts your message. So you need to supply 0.001 Ethers. Mind that in other EVM chains the fees differ. So you need to query the actual fixed native fee amount on every supported chain explicitly. Please don't hardcode these values. So let's go back to the incrementer command. So here we ensure that during the call to increment or increment with included gas, enough value has been provided to cover the protocol fee and the optional execution fee that you are willing to pay for the executor on the destination chain. After that, we need to calculate the exact execution fee amount. So again, the execution fee is the optional fee you are willing to pay to the executor of the transaction on the destination chain. And the execution fee is a portion of the asset you are going to bridge. So in our example, we are bridging the native blockchain currency of the origin chain. So say if we bridge from if we make a bridged call from Ethereum, we bridge Ethereum, and we must supply at least the protocol fee and the optional execution fee. But for the deBridge gate takes additional cuts off the additional fee of the bridged asset. It's around 10 BPS. Again, don't hardcode these values, but rather query it from the deBridge gate. So here we query the percentage the bridge gate will cut of the bridged asset. So expect to see 10 BPS here. So we see that we bridge amount to bridge will be equal to the execution fee, and the amount that we will receive after the bridge on the destination chain is the amount to bridge reduced by the 10 BPS. That's all about the preparations. Then we are going to construct the cross-chain call. First, we need to construct the submission outer params structure, which contains a lot of flags and operational fields. At least the submission outer params contains the execution fee, so we set it to the amount that we are going to receive after the bridge. We also set flags. There are a lot of flags that you can look up in our source code, but in this particular example we need to set two flags. The first flag is the proxy with sender, which tells the deBridge gate to expose the address of the caller in the original chain. If in case you don't set this flag, the check on the counter contract won't succeed, because the call proxy won't expose the address of the incrementer contract. And the reward is external fail, is the behavioral flag that tells the deBridge gate to revert the whole transaction in case the call to the counter fails. So there are two ways we can handle it. Say the call proxy makes a call to the counter and the counter fails for some reason. It may, if you set this flag, then the call proxy will fail too. But if you don't set this flag, then the call proxy will gracefully handle the failure of the counter and and mark the submission as successful. So so you can operate how the submission should be finished either gracefully or with failure. Then we set then the submission outer params contains the data field, that's the call data that we contain in the instructions that need to be executed on the destination chain. We already prepared them by calling the ABI encode. And the very important flag is the fallback address. Field is the fallback address. Here you must provide the address on the destination chain where the bridged money, bridged asset, will be transferred to in case of the failure. The bridge gate requires you to specify this address even if you are not going to bridge any asset. And lastly, the call to the deBridge gate send method is performed. You see that we provide the value with the amount that we provided during the call to the incrementer method. Again, just a reminder that the value must cover at least the protocol fee, which is equal to the global fixed native fee on the origin chain. And here are the arguments for this method. In the first argument, the token address, you specify the address of the token on the origin chain you are going to bridge to the destination chain. It can be either a zero address, and this means that you are bridging the native blockchain currency of the origin chain, or it can be the address of ERC20 token on the origin chain. Next, you should specify the amount you are going to bridge, the amount of the token specified in the first argument. It can be zero, so don't include the protocol fee to this amount. Just include the execution fee, and any asset you are, and any amount you are willing to receive on the destination chain. The third important argument is the ID of the chain you are willing to bridge this message to. The list of supported chains can be found at the chainlist.org or anywhere in the internet. Then you need to specify the receiver. This is the packet address the asset should be sent to, and the instructions the call data should be executed against. So we specify the address of the counter here. Other arguments like permit, use asset fee, and referral code right now are not important. You can find the what they mean in the documentation. And lastly, you need to encode the structure that we've prepared right there. So in case you made this call, the deBridge gate will validate all these arguments, and in case they are all valid, in case the value contains enough Ether to cover the protocol, the fixed native protocol fee, and in case the amount you are going to bridge is more than the value you have provided, then the message will be submitted and the sent event will be emitted. Right now I would like to show you how these two contracts are operating in the wild, in the mainnet chains. So for the purpose of this, I already deployed both of these contracts to the chains and configured them. I mean, I deployed the incrementer, I called set deBridge gate and add counter, so that these contracts already know about each other. And the same I did for the counter contract. I deployed this contract and call that set deBridge gate and add chain support, so they can operate with each other. Right now I will show you how these can be performed. Let's go to Etherscan. I deployed and verified the source code of this contract. So I deployed incrementer contract to the BNB chain. You can see the verified source code here, and I deployed the counter contract to the Avalanche. Let's try to perform the call. So I go to the incrementer contract, but before we start, I will show you the current state of the counter contract. For the purpose of this, let's go to the read contract section. And you can see that the counter, the state variable of the counter contract, already has the value 5. This means that I already performed several cross-chain calls to this contract to test if everything works correctly. Let's go. So just remember that the current value is 5. So let's go to the incrementer, let's go to the write contract subsection and find the increment method. Here it is. If I will check if the MetaMask is connected. No, it's not connected. I will connect it right now. Yes, switch the next network. Right now my wallet is being connected to Etherscan at the BNB chain. Right now we are going to call the increment method of the incrementer command. For those of you who didn't do this before on Etherscan interface, the first field is not the argument of the increment method. It's the amount of native currency you are providing to this method. This is because the increment method is marked as payable. I will show you. So here's the incrementer contract source code, and you see that the increment method and the increment with included gas method are marked as payable. That's why they are ready to receive value. That's why the interface of EtherScan shows this field. So I don't remember the protocol fee on BNB, so let's query it first. For this purpose, I will go to BScan, find the deBridge gate again, go to the contract tab, read as proxy, global fixed native fee has this value. It means that it is, yeah, so 0.005 BNB should be supplied to the deBridge gate contract when calling the send method. So I copy this value and put it to this field. So that's the amount of BNB I need to supply to increment, so that increment will pass this value to the deBridge gate contract to cover the protocol fee. Okay, and the first and the only argument of the increment method is the amount. So that the amount I'm willing to increment the counter property by. Let's say I want to increment by 10. So the current value is 5. I will increment it by 10, and the resulting value I expect to receive is 15. So let's call the increment method. I see the MetaMask pop up. I confirm the transaction. Yeah, let's view it. Let's wait a few seconds until it got caught. It's currently in the pending state. Yeah, the transaction has succeeded. This means that the submission has been accepted on the origin chain by the deBridge gate contract, but that's not enough. Let's take the transaction hash and go to the deBridge gate to the deBridge Explorer, where we can view the status of submissions. So we go to the deBridge.finance, open the Explorer, and enter our transaction hash. Inside these transactions there was only one submission. Here we can see it. It's this submission that was made during the call to the increment method. Let's open it. Yeah, we see that while I was talking, 12 blocks have passed, and the deBridge validators have started confirming this. You can see in the bottom of the page the list of the validators that have already confirmed and signed this submission. So we see that 12 signatures have been published to the deBridge server, and so yeah, it's time for the submission to be broadcasted to the destination chain. As you remember, we didn't cover the execution fee, the payment for execution on the destination chain. So we need to execute this transaction manually. For the purpose of this, the DEXplorer provides an easy interface for making such transactions. So I just so you see the claim button. I click on it. Something happens. I need to change the network. Yeah, I change the network to Avalanche, the target chain, and I will relay the transaction. Yeah, so the explorers construct the transaction where the call to the deBridge gate on the Avalanche will occur to the claim method. So I confirm it. Let's check the status of this transaction. Yeah, the transaction has been accepted by the Avalanche chain, and I suppose that the status of the state of the counter has been changed. So let's go to check it. By the way, you see that the transaction initiates a call to the deBridge gate contract, not to the counter contract, but to the deBridge gate contract, which should verify the message, check the signatures, and only if everything is valid, it will unpack the message and execute the call to our counter contract. So let's go to the counter contract and let's read it. I will reload the page. Yeah, you see that the counter variable has been incremented up to the expected value 15. Worth mentioning the events. Let's check the events of this counter contract. We can see that 1 minute ago the event with the name counter incremented has been emitted, which means that the counter has been successfully incremented. Let's check these values. So the new counter value is 15, that's correct. The amount the value has been incremented by is 10, that's the same, correct. The chain ID from, so the call has been originating from BNB, its ID is 56, that's also correct. And the initiator, it's the address who actually performed the call to the deBridge gate, is my wallet. You see 0x441. I will confirm it using MetaMask. Yeah, that's my address, 0x441. Yeah, so that's how the cross-chain call is handled by deBridge in manual mode. But in most cases, we want these transactions to be executed automatically. So we want to create a cross-chain call on one chain and expect it to be executed automatically on the destination chain. So we don't need to go to the D Explorer and construct this transaction for the destination chain. For the purpose of this, we need to supply some money that the protocol will pay to the executor on the destination chain. To show you how it may work, there is an increment with included gas method, which accepts the second argument, the execution fee. So the execution fee is a technical definition of the amount that the protocol will pay. So again, let's try to call it. No, before we call, let me tell you how to calculate the execution fee. So again, the execution fee is the part of the bridged asset, and if you breach the native currency of the origin chain, then you will receive the wrapped version of asset on the destination chain. But the currency on the origin chain and the currency on destination chain are incomparable. And also, it's important to understand that the gas price, which is the measure of execution of the transaction, the gas prices are different across chains. So we can't take the gas price of the origin chain and estimate the cost of the transaction on the destination chain. And what is more important, we need to understand the amount of gas we need to execute the transaction on the destination chain. So it's a quite complex topic, but for simplicity, let's take the transaction that we already submitted manually. That's it. So I go to the claim transaction on the Avalanche, open the details, and I see that it consumed almost 340 almost 500,000 of gas here, and the gas price was 26. So we need to multiply the gas for this transaction to the current gas price which we currently see, and convert it to the dollar equivalent according to the current price of the Avalanche. And then we must convert the amount back to the BNB native currency, so we can understand how much BNB should be provided to cover the costs on Avalanche. For that purpose, let's go to our calculator. So the gas price is 26. Let's take 30. Then we multiply it by 500,000 of gas. I take an extra amount of gas to avoid accidental spikes. And then so that's the amount of AVAX that you need to have to pay for gas, but we need to convert it to BNB. So we use the dollar equivalent. It's around $20. So we subtract it. Yeah, that's the amount of dollars we need to have, and then we multiply it by the price of the BNB. Yeah, that's the amount of BNB that you need to supply as an execution fee that will be passed to the bridge gate and then to the executor. So right now we can, after we know the amount of execution fee, we can craft another transaction. So again, how much BNB should be provided? Previously we provided only the amount of the protocol fee, which is 0.005, but right now we want to add the execution fee, so we specify more, which at 0.005 plus let's take 0.3. Yep, and this amount will be provided to the bridge gate. The amount we are willing to increment by is 10, and the execution fee we are willing to pay is 0.3. That's it. Let's send the transaction. Yeah, the execution fee should contain decimals, so we multiply the execution fee by the decimals. That's the amount. That's the inconsistency of the interface of EtherScan. In this field we can specify the human readable amount, and in this field we must specify the amount with decimals included. So let's try it. Oh yeah, I need to switch back to BNB. That's it, and right now I will write the transaction finally. Yeah, that works. Confirm. View my transaction. Wait until it included in the blockchain. Yeah, it was included. Let's take the transaction hash and go to the DExplorer again. Yeah, here is the submission. Yeah, already enough block confirmations have been passed, and we are now waiting for signatures from the deBridge validator services. So you see that it's pretty fast. Enough signatures had been already published, so 10 is more than enough to relay the transaction. But you see that I'm not going to send the transaction to Avalanche. I'm waiting for the automatic execution server to relay this transaction to the Avalanche. So you see that we are waiting for it. It may take some time because the claiming service must be ensured that the transaction has been included to the blockchain. But it usually takes a couple of minutes. Yeah, you see that I didn't sign the transaction on the Avalanche. It has been signed automatically. Let's check it. So I go to the claim transaction. I click on it. Yeah, you see that the transaction has been submitted from another address, not from mine. Mine is 0x41, and this one is the address of the smart contract, which is related to the transaction claimer, and the claimer with this address has been paid for the amount we have bridged to pay to it. And now let's go to the counter contract again. There it is, and check the current state. So I reload the page, read the contract. Yeah, we see that the counter again has been incremented by 10, and the current value is 25. Let's check the events. Yeah, we see yet another event has been emitted a minute ago, and the new counter value is 25 is correct. The amount it was recently incremented by is 10, and the originating chain ID is 56, and the initiator is again my address, 0x441. So two events that were emitted during this demo show how the calls can be corrupted and broadcasted across different chains, either manually or automatically. That's probably all for today that I wanted to show you during the demo. But I would also welcome you to our website, deBridge.finance, where you can find a lot of useful information and tools for developers. So go straight to the developers section, where you can find links to the documentation, to the API of our solutions that are built on top of the deBridge infrastructure. For example, tswap, the cross-chain swapping solution, uses deBridge contracts, but it is implemented as a separate product. You'll also find the tswap widget, which is useful for webmasters to integrate the cross-chain swaps right into websites. And for developers, there are two important tools that we open sourced. The first tool is Hard deBridge. Hard deBridge is a plugin for Hard framework to simplify testing and validating your cross-chain messages. So you saw that the deBridge infrastructure is quite a complex stack, and it's almost impossible to replicate it locally. But this plugin simplifies it by providing an emulated environment which replicates the deBridge infrastructure on your local machine. So just install this as a package to your product, where you use the Hard framework, and then you will be able to run the deBridge emulator locally, which deploys the vanilla source code of the deBridge Gate smart contract, so you can test the calls to it using your local blockchain. And it also provides some extension to the test framework of Hard, so you can write tests again the contracts you are developing that should communicate with deBridge Gate contract. By the way, the cross-chain dApp that I was talking about is built solely on Hard and Hard deBridge. So if you go to the deBridge cross-chain dApp example, you will find that tests using the Hard deBridge plugin to test the communication between these between each other. Also, we developed a software development kit, DSDK, which is also open sourced. It's a production ready product for complex installations of complex products, complex protocols, who need a graceful way to manage and handle cross-chain submissions. So simply speaking, I show you how I submitted a message on one chain user using Etherscan and checked the status of this message using the Day Explorer. But probably you want to do this programmatically without going to our interface, without relying on our infrastructure. And here's where DSDK will help you. It provides a lot of handy methods that are useful for creating submissions programmatically, checking the status of submissions again programmatically, and if you don't want to pay the claimer and you would like to, for example, create gasless submissions or submit them on behalf of users, claim and relay submissions on behalf of users, you can use again DSDK to programmatically make this happen on your product. So DSDK, again, a production ready product for complex protocols. So feel free, but it's quite easy to use, so you can use it in your pet projects, and I encourage you to use it in your protocols and products that you are going to build during this hackathon. So that's all for today. Thank you for watching. I hope to see you all in our Discord channel, in the Discord channel of ETHOnline. So feel free to ask me some questions and see you soon. Bye. Good luck.